Okay, so we have a hash table, which is an array indexed from 0 to capital N minus 1. And we have a hash function. And our goal is that when we insert items into this hash table, we want to place it at the hash value of that key. So this will give the index where we place an item. Now, we can reduce the probability that we encounter a collision, meaning we have two totally different items that happen to map to the same location. We can reduce the probability that that type of collision occurs by picking a good hash function, as we saw in the previous video. But we can't always guarantee that no collisions will occur. So we still have to consider what happens when we get two different elements that map to the same cell. What should we do? There's two different approaches to handle this. One is a very straightforward approach. This is called chaining, where we have that every cell in our hash table stores a list of items rather than a single item. So every cell stores a list. Maybe that list is empty, but it could have multiple items in there. So for example, if we go back to our employee records hash table where we had employee records stored based on the last 4 digits of a social security number, if we had two different items, two different people who had the same last 4 digits of their social security number, using chaining, we would just add that other element to the end of our list. So when we encounter a collision, we handle it with chaining by just creating a chain of all of those items that have the same hash value. So if we get another item which has the hash value 0001, we just add it to the end of this list. And if we get another one, we add it to the end of the list, and so forth. So that's how we would handle collisions using chaining. The downside of this is that it requires extra memory outside of the table. So we have our table of n elements, but then each cell stores a list. So this requires some extra memory. Open addressing is created in order to be rid of that requirement of we don't need any additional memory outside the table. So this is open addressing. And the idea behind open addressing is that we don't have a list at every index of the table. Instead, here's our table. In fact, we could draw it horizontally instead, but we only store at most one item at each cell. And if we encounter a collision where another item belongs at that cell, then we just have to figure out some other different cell in order to place it. So the upside of this is that it doesn't require any additional memory, but it makes the searching and removing operations more complex because an item doesn't necessarily belong where its hash value is. It might move around. And there's a few different types. We're going to talk about linear probing and double hashing specifically. So to handle collisions with open addressing, one approach is the linear probing. And linear probing just means that we're just going to place the item in the next available table cell. So specifically, that formula is we try at this index every time. So beginning with I equals 0, this is kind of like the number of attempts that we've made so far. So with initially 0, we're not adding anything else here. We just check at the index of our hash value. So k is our key. We want to insert an item with key k somewhere in our hash table. We take the hash value, and then we use our just mod n to make sure that we're within the bounds of our array, in case this increases too much. So our hash function already outputs something within the bounds of our array, but then sometimes we add something to it, so we have to make sure that we stay within the bounds of our array. So this mod n will just guarantee that if we go outside the bounds of this array, we're kind of circularly wrapping back around our array where necessary. And every time we encounter a collision, we increment I. So if we tried at index h of k, this is the hash value of k, and something was already there, then we're going to try h of k plus 1. And if something was there, we try h of k plus 2. So this has the effect of starting at a particular index, and then if that's occupied, try the next index. If that's occupied, try the next index. So this is linear probing. So let's do an example here of, let's say we were to insert these keys in this order. And when we go to insert 18, so I have here just some pre-computed values. So if our hash function, let's say our hash function is x mod 13, since we have 13 elements in our hash table, then we would insert the key 18 at index 5. 18 mod 13 is 5, so we'll place 18 here. And then 41. 41 mod 13 is 2, so we're going to place 41 here. Then we insert 22. 22 mod 13 is 9, so we're going to place 22 here. And 44. 44 mod 13 is 5. Okay, so here's where things start to get interesting. When we go to insert 44, its hash value is 5, same as 18, and this is our first collision now. So with linear probing, we're going to try the hash value of 44 plus 1. So this will be 5 plus 1. This is the same as saying, okay, we tried index 5 was not available, so we're going to try just the next index. Is this one available? And there's nothing in there, so we can place 44 here. Then we go to place 59. 59 mod 13 is 7, so we'll try at this index, which is available, so no problems just yet. And then 32, we should place this at index 6, because h of 32 is 6. And now we run into another collision. So we try to insert at index 6, this is occupied, so now we move to index 7, that's also occupied, we move to the next one. Now we finally find a free available space, so we insert 32 at index 8. Then we go to insert 31, we try at index 5, because h 31 mod 13 is 5. So we start here, this is occupied, we move to the next one, it's also occupied. We keep moving down until we eventually find an unoccupied cell. Now we can place 31 here. Then we insert 73. 73 mod 13 is 8, so we're going to start at index 8. This is occupied, so with linear probing, we move to the next one. This is also occupied, we move to the next one. Also occupied, so we move all the way to index 11. We insert 73 here. And just to show you what I mean by how this works kind of in a circular fashion, let me show you, let's say we were to also insert, I'm going to add a few other keys to insert. Let's say we insert after this, we insert the keys 12, and then 25, and then 38. So 12 mod 13 is just 12, we would put it here. 25 mod 13 is also 12, so we would try and place it here, but this is occupied. So we're going to try at the next index, but don't forget we're taking all of this mod n, which means we try at index 13, but 13 mod n will give us 0. So we just kind of wrap around the array. So we'll put 25 here, and same thing, 38 mod 13 gives us 12, so we would try to insert 38 at index 12. This is occupied, so we move to index 0. This is also occupied, we move to index 1. So we finally insert 38 here. So this is how linear probing works. You may have noticed already that this tends to cluster items together. So we have kind of this big cluster here, albeit our table is kind of full, but the same problem appears even for very large tables, that we tend to get this cluster because anytime we have something that collides within this entire range, we just make our cluster even longer. So then that causes an even longer sequence of probes, and then our cluster just keeps getting a little bit bigger and a little bit bigger. So let's think for a moment, before we move on to the other open addressing technique, let's see how we would do things like find an item based on a key or remove an item based on a key. So this is how we would insert items using linear probing. Now, how would we find an element based on a specific key? Let's say we wanted to find, what would be a good one here? Let's say we wanted to find 31. So if we want to find the object that has the key 31 associated with it, we can use our same hash function. So 31 mod 13 will take us to index 5. And then we can just compare to see, does this key match the key that we're looking for? And if it does, great, we're done, we can just return that. But if it doesn't, we have to be a little more careful because maybe we had to place 31 at a different location. So if they don't match, because we know we're using linear probing here, if we don't find a match just yet, we're going to move to the next index. And do these match? They don't, so we're going to move to the next index. If they don't match, we'll move to the next index. And we're going to keep moving to the next index until either we find that key we're looking for, or we encounter an empty cell. So maybe we're looking for the key 19, for example. So we'd start here, we'd work our way all the way around, not find it, and then encounter an empty cell. And then if that happens, we know, oh, okay, if we had that key, we would have placed it here in this available position, so we can return that it doesn't exist in our table. So this is the main idea behind searching with linear probing. So we figure out what index we should start at. This is the hash function of our key. And then we can keep track of how many times we've tried to do this as well. Because if we've gone around our entire table n times, then maybe our table would be full, but there are no empty cells available. So we want to make sure we don't exceed how many elements are in our table either. And then we just keep checking to see, okay, at this index, at the hash value of our key, does this match already the item that we're looking for? If it does match, we can return that element. If there's nothing stored there, we've encountered an empty cell, we can return that the key doesn't exist in our hash table. But if there is something stored there, it just doesn't match the key that we're looking for, we increment that, okay, now we try the next index. And we increment how many times we've tried this so far until we either find the key we're looking for, we find the next available cell, or we realize that we've iterated so many times that we've already gone through all of the cells of our table. So this is how we would find an element. Now what if we were to remove an item? So let me go back. Now let's say we remove, let me remove 18. So we can definitely find 18, that item that we should remove, using the same method that we did to find an item, right? So we can start at the particular index, compare keys to see if they match, and they do. If they didn't, we could keep moving forward until we either find it or find an empty spot, meaning that it doesn't exist. But once we do find it and we know, here is that cell that we want to remove, when we get rid of it, we have to be careful that once we get rid of it, we run into the problem that maybe 18 was causing other keys to be placed later because 18 was there. So if we were to remove 18 and then after that look for 31, we would find that, okay, 31 mod 13 is 5, so we should look for 31 here at this index 5, and now this is empty. Now before we had 18 there, which caused 31 to get moved over all the way to index 10. But we have to be careful when we remove an item to keep track of the fact that there used to be some item here. So if we go to look for another item again later, we have to kind of mark this cell specially so that we know there used to be something here, so if we haven't found that item we're looking for yet, we should just pretend that there was something else here before and keep on searching. So this is the idea behind removing with linear probing. So when we go to remove an item, we search for it, we're given that key. If we find it, then we're going to remove it, but we're going to replace it with a particular, just a special item to indicate here. This available just means that this is empty, it's effectively empty. We can insert something new here if we want, but there used to be something here before. So later, when we go to find an item or insert an item, if we go to insert an item, we can use these specially marked available cells as they are effectively empty. We can insert an item there if we want. But if we go to find an item, we want to treat these available cells as something where there used to be a key there. We should treat it, kind of continue looking for that key if we haven't found it yet. So when we insert an item now, we assume that these available cells that we've specially marked treat them as if they're empty, and when we find an item, we treat these available cells as if they are filled. Okay, so that's linear probing. With linear probing, if we encounter a collision in our hash table, maybe this collides here, then we just try the next one, and then we try the next one, and we try the next one, and we circle around the array if we have to, just trying the immediate next consecutive cell. The problem with linear probing is that we tend to get these clusters. It has this, what's called primary clustering, where we get a lot of them kind of jumbled up together, which causes these larger and larger and larger clusters. So in order to prevent that primary clustering from happening, we have a different approach to open addressing, which is called double hashing. So like linear probing, it uses one hash value as a starting point. This is our h of k. And then it repeatedly steps forward some interval until a desired value is located, an empty location is reached, or the entire table has been searched. But the interval over which we skip to find the next available cell is decided using a second hash function. And this is an independent hash function, hence the name. So unlike the previous one, the interval itself depends on the data. It depends on the key that we're given. So even values that happen to map to the same location, have the same hash value for the function h, they might have different bucket sequences, the series of cells that they would check consecutively, because they would have different hash values according to D. So this minimizes the possibility of repeated collisions. So we continue to take, just like we did before, this result mod n, because we want to make sure that even if we increase from our starting hash function, if we increase some value, we don't exceed the bounds of our array. We're always going to start initially at whatever our first hash function was, and then if this cell is occupied, we'll keep track of how many times have we tried so far. This is I, the number of attempts that we've made so far, unsuccessful attempts, and increase this every time we have to, every time we've stopped at a cell and we've collided with some other thing. But we're going to multiply this value with another second hash function, as long as this second hash function isn't 0. So again, we have to assume, in this case, just like we have before, that the size of our hash table is prime. And this is particularly important here for double hashing, because it will guarantee that even in the worst case, if we collide with every other element, that we are guaranteed that we'll encounter every cell of our table. So let's see an example of this. Let's say we have a hash table of size 13, which means they're indexed from 0 to 12, so we've got 13 elements. And we have two hash functions. This is our first hash function, our primary hash function, and this is our secondary hash function. And we're going to insert the following keys in this order. So this will start off looking kind of like what we did before. The only difference will be in when we encounter a collision, where we place the next item. So let's try and insert the key 18. So I have here, again, pre-computed values. So here's the h of 18, and here's d of 18 if we need it. We might not need this. So h of 18 is 5, which means we want to place 18 at index 5. So we're done with that. Now for 41 mod 13, this is h of 41, is 2, which means we should place 41 at index 2. Okay, we have no problems so far. Now for 22, h of 22 is 9, which means we got to place this at index 9 if we can. No issues. Now for 44, we want to place 44 at index 5. This is its first hash function. And now, finally, this is where things start to get interesting again. Okay, so we want to place 44 at index 5, but the problem is 18 is already there. So we have our first collision. So rather than moving over one spot, this is how linear probing would have worked. Just try the next cell, next cell, next cell. Double hashing will skip over some interval and try not the immediately next cell necessarily. Maybe this is 5 positions over, 6 positions over or something. This interval over that we're going to skip is based on our second hash function here. So this is that second hash function we're using. So we haven't actually used it so far, we haven't needed it, but we're going to start using it for 44, because now we have a collision, we need to know what its second hash value is. So this is 3, which means every time we encounter a collision, we're going to move over 3 positions. So this isn't an index, this is an offset. So we had started at index 5, this was the first hash function for 44. And since this is occupied, we're going to move over 1, 2, 3 positions. We're going to skip immediately to index 8. So this is our starting hash value offset by this many cells. So we're going to try at index 8 now to insert 44. And this is free, so we're okay to insert there. So now we try to insert 59. 59 belongs at index 7, which is free. 32, its first hash function is 6, so h of 32 is 6, which means we'll want to place it here. And 31, h of 31 is 5, we're going to want to place it here. Okay, this is where we get now another collision. So we want to place 31 at index 5, but this is already occupied, so we're going to use this secondary hash function. So since index 5 is occupied, we're going to repeatedly move over 4 spaces until we find an empty cell. So for inserting 31, we're going to try at index 5. This doesn't work, so we're going to move over 1, 2, 3, 4 positions. We're going to try at index 9. This is also occupied, so we're going to move over 4 positions from this one. So now we're going to try 1, 2, 3, wrapping around the array as we need to, 4, until we find index 0, which is free. So now we can insert 31 here. Notice that this is what I meant that why this reduces collisions is because we're using the secondary hash function in order to determine the interval over we have. So for example, 44 and 31 both map to the same value, but you'll notice that 44, we went first to index 5, then to index 8. So this was a different probe sequence that we tried. Whereas with 31, we tried at 5, and then we tried at 9, and then we tried at 0. So this was a different sequence of cells that we tried. And that sequence of cells, that interval, is based on the second hash function, which is also based on that key. Okay, so last one here, we've got 73. H of 73 is 8, so we're going to try and insert 73 at index 8, which is occupied. So we can't insert here, so we're going to use the second hash value for 73, which is 4, which means we're going to move over, since this was occupied, we're going to move over 4 positions. So 1, 2, 3, 4. And we're going to try here, which is free. So this is how double hashing works. We can, just as we did before, if we want to find an element, let's say we want to find 31, we would do the same method we did before. Use the same hash function. H of 31 is 5, so we'll try at index 5, kind of the same way that we tried to insert it, basically. If this doesn't match the key that we're looking for, then we'll use our second hash function and move over that many cells. So for 31, because its second hash function is 4, we would move over 4 cells to 9. If that doesn't match it, then we're going to move over another 4 cells until we either find the key that we're looking for, or we find an empty cell, in which case we know it's not there. We would have placed it at that empty cell if it existed. Or we've wrapped around the array. We have probed a total of n elements, guaranteeing that we've already tried every single cell. In which case, if we still haven't found it, then we return that it doesn't exist in our table. And similarly, if we wanted to, let's say, remove 18, just like we saw before, we can find where this element is using the same approach, using our first hash function and our second hash function. So we can find that 18 belongs at index 5 because h of 18 is index 5. And now we're okay to remove it, but when we remove an item, we have to mark it kind of carefully to indicate that this is an available cell, meaning If we are trying to find an item and we encounter an available cell, we should treat it like there's something there and keep going. If we go to insert an item and we find an available cell, we should treat it as an empty cell and that we can insert a new item there. Okay, so how does this compare really to chaining? So open addressing versus chaining. We saw two different approaches to open addressing, linear probing and double hashing. Double hashing is much better because it reduces the likelihood of the sort of primary clustering that we encountered. But in general, we have, in the worst case, any of the find, insert, or remove that we would do on a hash table could be linear time. And this would occur if we were so unfortunate as to have every key collide. So that's still the worst case situation, but we can show that on average that doesn't really happen all that often because we're careful with how we pick our hash function. So one thing which affects the performance of our hash table is this load factor. This is the fraction of how full our hash table is. So we have little n elements in our hash table, but our hash table could support capital N items. So this is a fraction of how full our table is. And we can show that if we're using open addressing, that the number of expected probes that we would take for, say, inserting an item or finding an item or removing an item is 1 over 1 minus alpha. So if we had that alpha was 0.8, meaning our table was 80% full, then the expected number of probes, if we go to insert, is 1 over 1 minus 0.8, which is 0.2, which gives us 5 expected probes. So this is still constant. And similarly for chaining, the expected number of probes for inserting or finding or removing is 1 plus alpha. And again, alpha is constant because this is the how full our table is. So this means that the expected running time of all operations is constant. So this isn't the worst case. The worst case running time is still linear, but we're saying that the odds that this really actually happens is low. We can expect that our operations will run in constant time. So the average runtime for all unordered dictionary, these hash table operations, is constant. So in practice, this is actually really fast, provided that our table isn't very full. So if we are using, let's say, chaining, this is good in the sense that this is a pretty simple design, easy to implement. It's also not as sensitive to our hash functions or load factor. In fact, it can even support a load factor of larger than 100% because we could store, maybe every cell stores 2 items, for example. But it doesn't have as good memory usage. Open addressing has better memory usage, but then it requires a little bit more careful selection of our hash function in order to avoid clustering like we saw with linear probing. And it also degrades after a certain point. So if we have a load factor larger than 70%, this doesn't really perform as well. So, and unfortunately can't even support a load factor of larger than 100% like chaining could, because we only store 1 item at each cell. So if you have any questions, post on Piazza, reach out, let me know.